because we get into the main topic of today's lecture and now start sharing. So today we'll end with the nonlinear equations. So we'll go through again Newton-Raphson. But now we will go not only to the Newton-Raphson in 1D. So in the case that we have just one equation, nonlinear equation that we are solving with one variable, but we will get into the having multiple equations and multiple variables, and then we apply at the end to some simple mechanism. But okay, let's go through the topic. So just a quick recap. This is our problem that we want to solve. We want to solve equations in the form f of x equal to 0, and where f of x is some nonlinear equation. So typically, but just by looking on it, it's not so easy to find the solution. And of course, we'll use here on the scores some numerical methods to solve this. And as a recap, also this problem is called root finding, and we will use it primarily for kinematic analysis of mechanisms. Brute force method, I think that we talk about this. Does it require any comments? I hope that it was quite a while, but simply as the name suggests, in brute force method, we just search the whole space that we are available. So in this case, we have a function, then we have stored as a bunch of points. And we are just going through all the pair of the points to find when it crosses 0. And when it crosses 0, then we know that between those 2 points, we have a root. And then we use some simple linear approximation, interpolation to get the value of it. And we go through the algorithm, and we have seen how it works. Then we discussed a little about prior allocation. As I remember, the result of this discussion was that it helps, but the effect wasn't extremely significant for our simple problems. So we decided that maybe it's better to keep the code simple, especially that prior allocation for this kind of problems is pretty tricky. And then we went to Newton-Raphson's method. So, and this is the method that we'll go with. We start with this 1D solution. When we have laser pointer works. When we have the function of one variable, one single function of one variable, and we have seen it. Then we have learned how it is developed. Do you remember what is the base for this approach? Okay, yeah. Exactly. Yeah. So we have some starting point. Then because it's non-linear function, and we really like to solve linear problems, because it's easy, straightforward, and doable. So the question is how to best approximate this nonlinear function as linear one. And we have proper tools for it. So for 1D is just having a tangent, because we know that in practice, if we have tangent of the function, and if we select enough small surrounding for this tangent, the tangent corresponds well with the value of the function. Of course, here, as we go further, this linear approximation get worse. But in practice, it is good enough to bring us closer to our solution. So we get the point, find value of the function, then we approximate this function by using tangent. So then we solve for a tangent. So we are looking where tangent crosses the zero, and this is because this is linear equation. We can do it very easily, yeah. And we check if this is our solution. Like in this case, the next point is not clearly not our solution. It's somewhere there, yeah. So we just repeat the procedure, yeah. So again, we treat it as new initial point, find the value of the function, approximate with tangent, find another point, uh, and we treat this point again as our initial solution, and we repeat it until we get to zero. Yeah. And here, the algorithm that I described can be written in such a way, yeah, because, if we approximate our function, we have value of the function at this point plus the tangent, and we solve for it. We can solve it for x, which is our new solution, and solution for x give us simply this equation, yeah, and we have to loop this equation until we get the solution. Just to be short, let's take a look on implementation. Okay, I remember that we discussed about Newton-Raphson, but we also do you remember if we discussed also about those codes for Newton's method? Okay, I think that yeah, you are also not sure, so let's go through it quickly. I think it's better to have it covered because again, after meeting for 5 weeks, it's hard to expect that you remember such details. I don't remember them as well, but here is implementation of the simple Newton's method. It's called naive Newton, yeah, because it just implements directly this code, yeah. We'll see why it's called naive because soon. But about the code, yeah. So as you can see here, it requires 4 parameters in general to work, yeah. First one is f, is just our function, yeah. So because a function that we will use to find the solution, that as it needs to calculate also the tangent, yeah, then we have to provide it. Starting value, I think it's clear, yeah, it's iterative procedure. Typically, iterative procedure needs to start somewhere, yeah. So we have to provide some good approximation from our solution, yeah. Especially as you can see for description of this method, yeah, it's just looking for one solution, yeah. So like with this brute force, where we have this example that we have multiple times the function crosses the line, yeah. Here with Newton's method, it's not the case, yeah. Here with the Newton's method, simply we can get one solution, yeah. Is it clear? Oh, it's pretty clear, yeah, because we just provide one initial value and then it will converge to something, yeah. But in many cases, this is okay, and in our case, this is fine, yeah. Can we somehow mitigate this kind of behavior if we need to find multiple points? Hmm? Yeah. Somehow, yeah. So So algorithm, yeah. So the algorithm builds on the solution, yeah, because here was the solution just to check the different initial values and see if it converges, yeah. So the Newton-Raphson is pretty popularly used, yeah, but it's rarely used as the only searching method, yeah. We'll use it, but because of the characteristic of the problem that we have, yeah. And typically it's used rather in the way that it's combined with different method, yeah, because the characteristic of this Newton's method is that it converges very quickly, yeah. Uh, you will see that to get from this point that it's really far from here, we need like, I don't know, maybe 7, iterations to get to the point. And when we are close, we often need 1, 2, 3, yeah. So it converges pretty quickly. And typically, the problem of finding these initial solutions is done by different algorithm that it's looking where approximately could be those zeros, those roots, yeah, and then gets closer, provides some initial value, and then makes the last few steps using Newton's method for fast convergence. Yeah. So, for example, in this brute force method, yeah, we could search for the solution with some sparse grid, yeah, and instead of using this linear interpolation when we are close to the solution, we could then use Newton-Raphson. Yeah, typically a little more sophisticated methods are done with than this brute force, but on the other hand, we have multiple zeros. It can be pretty tricky to find all of them. But okay, this is a little side note. So getting to Newton basic implementation, there is also fourth argument, which is a tolerance. Yeah, because iterative method. So it's typically it needs some initial conditions for work, yeah, and it also needs some condition to stop. Yeah. So we assume that if we find the value of the function close enough to our tolerance, that is typically a small number, that we assume that is our numerical zero. Yeah. And the implementation is pretty simple. We assign, for example, x to our starting solution, check if our solution is not already close enough to zero. If it's not, here in line 4, we just run this equation, yeah, that we have here. Yeah, so approximation with tangent and solution for the next point. Here it displays the point, but it's only for our visualization to see how it works. Yeah, typically you don't have stuff like that in your algorithm, and that's all. Yeah, and at the end, when this while loop breaks, yeah, stops, which means that we find the solution within the tolerance that we want. We just assign the solution to our results and a function. Yeah. Okay, and here is solution. Here is the example with the demo for the case on our slides. Yeah. So here we have, maybe just do it like humans. Yeah. More readable. Dots are fine. It's not a big issue. Yeah. So here is our function. Yeah. Uh, x times x minus 9. Yeah. Uh, so x squared minus 2. So plotted as here. Then we need to provide the derivative. Yeah. Here it's rather easy. So it's 2x, of course. And then we just run this naive Newton implementation by providing function, its derivative, starting point, and some tolerance. Yeah. And just let's run this code. Yeah. So it didn't take too many iterations to reach the correct solution. Yeah. As you can see, we start with 1000 and immediately we get to 500. Yeah. Then we have the step again to 250, have them multiple times. Yeah. And shortly after we get to the solutions that are near to 3, yeah, and I suppose that this was just barely below the tolerance, yeah, that's why here, due to limited number of the digits that we can see from MATLAB, it shows this number twice, yeah, but then we can see that we get reach the convergence, yeah, with expected value of the 3, and of course, because of the tolerance, we get some here, still some garbage values. But typically, we don't care about this, yeah? Or if we care, we should know, and then we can use tighter tolerance. Because, of course, we can use tighter tolerance, like 10 to minus 12. In this case, it should work no problem, yeah? Rerun the code. And as we can see, we get one more iteration, because as we compare with the area, we get 3, 3, yeah. And then we get one more iteration, and we get the correct result. Is it perfectly correct? Most likely not, yeah. If we'll use this fprintf, I think it was %.16g or something like that, and show xr. I hope that I remember this well. Okay, yeah. So get correct result, yeah. So this is nice. I think this is possible in this case simply because 3 can be represented exactly using this floating point arithmetics, yeah. Why, if you were... It doesn't really matter, yeah. Because G, the difference between F and G, if we are here, that G shows the most compact representation requested. Yeah, so it shows 3. It means that it drops all the zeros. Yeah, and with F we can see explicitly all those zeros. Yeah, yeah, but both should show the same if there would be some remaining parts. Any questions? Issues, doubts? No, perfect. Any questions from the audience? I cannot see. Good. Okay. So as I can see, I already described about the algorithm, but the rest of the algorithm is here. But we already have seen the implementation. Yeah. So it's again the same iterative solutions, and then check for if we are at the 0. Yeah. However, Newton-Raphson has some issues. Yeah. So it converges quickly, but the function must have certain characteristic for it to work. Yeah. So it can be seen nicely with this hyperbolic tangent. So here is another demo that runs Newton-Raphson with hyperbolic tangent. I think then firstly we have to run it with that value. Yeah. So okay, the code is the same, just the function is the same, is different. Yeah. Of course, you don't have to remember what is the derivative of a hyperbolic tangent. I also don't remember. I just check. I suppose that I check it with some tables of derivatives, but I'm pretty sure this is correct. So okay. So let's run this code. And by the way, solution for hyperbolic tangent, if you don't remember, is 0. Yeah. So it just crosses 0. Okay. You don't have to remember. We have plot here. Yeah. It crosses, its root is 0. Yeah. And it has only one root. So here, as we can see, nothing special. Yeah. Newton methods converges. Yeah. Within 1, 2, 3, 4, 5, 6, 7 steps. And converges pretty rapidly. Yeah, even that we requested the tolerance below 1 10 to minus 6, we get the solution up to numerical precision 10 to minus 15. But it's at least partly coincidence. Nothing special. Yeah, but when we use 1.09, yeah, with this method, that some other things happens. Yeah, so what has happened? What does it mean? Yeah, yeah, it's other case. We can see it by because it changes the sign, but the previous solution was also oscillating. Yeah, if we check this solution, it's also oscillating. Yeah. How it's called this phenomenon in numerics? Do you know? Yeah, divergence. Yeah. So it didn't converge to the correct solution. Yeah. So yeah, exactly. We get this kind of divergence. And so the fact that it's oscillating is not a big deal. Everything oscillates in the life, as we have learned on ODEs, on the stuff that we talk with ODEs, yeah. But the issue is that it oscillates, but also, as you can see, it increases uh, amplitudes and gets further and further away from the solution. Yeah. So when we were using 0 point in this 10 to minus 8, yeah, we get the values that are closer and closer with each step to 0. Yeah. There may be on the other side of the axis, like here, yeah, but still they are much closer to 0. But when we are using the solution, right from the start, it starts getting further away from the solution. Yeah. And because it's getting further away, then we just get out of the reach of the numbers that we can handle within our limited precision. Yeah. So after 10 to 11, which of course it's nonsense, yeah, we get to infinity. And then because we want to operate on infinity, we get not a number, which is clear the error. It's nice that it's at least stops, yeah, because then it could also, just keep iterating. And solution is not a number, so nothing useful. And this is because of the characteristic of this function, yeah. Simply, uh, here, when we use the 109, yeah, simply it gets, the tangent gets further away and it's diverged just here. So it's not nice, yeah. I think that, as I remember, there are even functions that you cannot use with this method to find solution because they diverges right from the root, yeah. But again, for most of our problems and all the problems I have seen, that we are dealing in our practical engineering, Newton-Raphson method is good enough to find the proper solution. Yeah. So typically it diverges because of the other reasons, but it can diverge. Yeah. So engineering approach is that Newton-Raphson works well when we are close enough uh, to our root. And then when it's close to root, it works very fast and very well. Okay, so this is the approach that we have, engineering approach to use this method. So either like in our case, when we will be analyzing the kinematics of the mechanism, we have to find the solution that is close enough to the real configuration of the mechanism to converge, yeah. And then even if we progress with time, we are always close enough, yeah. So that's why it works. And if we are in the case that we cannot find somehow the solution that is close enough, we should find another method that can find this solution, yeah, like for some random search, yeah.
For instance, tan x plus 5 independently converge then
Uh,
because it's not going to minus plus minus plus instead being constantly in the plus.
I think it doesn't matter that it goes to plus and minus. And if you add 5, won't we just, you mean that we will switch?
That's it. Not there, not there. Outside.
Yeah, yeah, but if we add, yeah, then I think that won't cross 0. We have to add 5 here. I hope it works. I don't remember. Yeah. So you would like to have something like this, yeah? That, for example, it's only negative, yeah, with respect to 0. Or minus 5, if you want to be positive. Yeah? something like that. So that we have a function that crosses it at 5. So even if we start here at 6.09, that will get positive numbers. Yeah. Okay, we can check it, but the behavior will be the same because we are just shifting this, and it has nothing to do with getting positive, negative. Yeah. What is important is that we get closer or further from our solution. The solution is 5. Yeah, if we add here -5. Yeah. So of course here we have -5. Yeah. And then we'll have 5 plus, okay, not percentage, 5 plus 1, let's say 0.8. And then it should work as expected. Yeah, close enough. The same characteristic. Yeah. Also, you can see oscillations with respect to root. And then when we add 0.9, the same. Divergent behavior. So yeah, if we do some scaling, then maybe we can make it behave better. Yeah, because if we do scaling, that we are effectively moving this point further away. Is it clear? Yeah. Then with scaling, like if we put, so again about, if we use something maybe like 5 times, or 1.5, it's, I think that I always, miss at which direction do. I think that we have to scale in another direction, So if we scale it with 0.2, it's rather this way. No, I think it was correct. Let's just check. Yeah. Oh, no. Okay. Now we are scaling in this direction. We have to scale the variable. Yeah, because now we just scale it here. Yeah. So I think it doesn't change a thing. We have to scale variable. Yeah. Yeah. That's true. Yeah. Now we are able to get more desired behavior. Yeah. Yeah. With this kind of function, it will work. Yeah. So scaling, we can perform scaling. Yeah. And if you put scale here, so then we have here 0.2 times then we are moving this point further away. Yeah. It takes quite a bit, but it finally converges. Okay. Okay, perfect. Any questions? I made this another demo that plots the line. If you still need some visual aid on why this is an issue for the program. Yeah. And yeah, I think it's better to run this in debug mode to see what is happening. Yeah. So if we put uh, stop here, yeah, for our debug. So now we can see how it works. Yeah. So because here we can see the tangents. Yeah. And first few steps doesn't look so bad. Yeah. So if we run it, what is the command for continue? Okay, run. Let's see if it works here. Okay. Yeah. So if we can see here, yeah. So we find point here. Again, use it as a new initial value find point here. Yeah. And here we can start seeing the issue that those tangents looks for this resolution kind of parallel. Yeah. So you can already see that we are start to, having some issues here because they should get closer and closer to the solution, those tangent, yeah. But now they are parallel, yeah. So at this stage we cannot see even yet, yeah, because the differences are small if it will converge or diverge. Because if you use 1.08, the first two tangents will be almost identical. But with the third one, yeah, the coloring maybe it's not the best. You can see that the third one is above the first one, yeah. So it start getting with our points further and further, and the more points we get, yeah, the more obvious it it is, yeah. So here with this tangent is already far away, and it doesn't seems like it wanted to get back. And here the issues are, pretty apparent, yeah. That because this point is already so far away for this function, this tangent is almost like, horizontal. Nothing good came out of it, yeah. So then we get this point that it's 10 to 11, and then it stopped working because it simply breaks. Yeah. Okay. But now I can see that I should have here some, yeah, quiz. Okay, so someone already answered it. So as you might remember, we had some quizzes here, yeah, using the Socrative. And yeah, so here is the code. The ROM is the same, I believe, so that's why some of you has already found it nicely. So today we have just a few questions regarding to this problem, but the rules are the same. I have to think about, because I believe that, that did Alexander make some quizzes for you?
Something different, like steps.
Yeah, I believe so. So did you like it? Did you enjoy it?
It's used for like basically just getting an information like how many students knew this or that.
Yeah.
Like this a little bit more, I would say. Like basically just questions related to what is instead of just basically questions getting information basically what the students know.
Okay.
Different things basically.
Yeah, that's true. Let's see. Not, let's wait a minute. Okay. Anyone that needs more time to answer this question? I think it was already last time, but it's not big, or maybe not. I don't remember so detailed, but it's not important. Every answer counts, yeah. Because here clearly I can see that that we have another question that is related to this topic. Yeah, so directly to this problem with hyperbolic tangent. So after you answer this, we will go to the next topic. So by the way, how was, the last week with Marek? Because, I gave him some my older slides like for 2 years ago. Okay, not that they changed so much, yeah, but for reference, and as I understand, he used it directly here. Okay, of course, why not? Yeah, they were relevant. So yeah, maybe if it makes it even easier for me to follow what happened and give you some insight of what will came next. But any comments to this?
Just received the slides like on Monday or Sunday.
Yeah.
2 days before.
Yeah, because he arrived just on Sunday. I mentioned to him that it would be nice, yeah, because I had this traveling, so I couldn't join you in any way. And I think that I will still have one more traveling during our course. So I think in 2 or 3 weeks, yeah, we won't have classes, yeah. So I thought that it's simply too much, yeah. One per semester, I think yeah, it always happens, yeah, because of whatever reason, yeah. So being sick of traveling, in my case, it's mostly because of the traveling. So I thought it's too much. Even I hope that it's only one, but yeah, but okay. So let's just wait a few seconds and.
Just a little dry. It's from
Hmm?
the content of the last one was a little dry.
Oh yeah, it was fully theoretical. Yeah, that's true. Yeah,
Like he presented it well, but it just
nice. But still, you still fall asleep. Yeah.
yeah.
Yeah. Okay. Perfect match. Wow. Yeah, so that's nice. Okay. We need. So it's also the case that we need maybe improve at least a little this method for our algorithmic news. Yeah, at least we would like to check if it converges. Yeah, if we get some erroneous results. Yeah, like here not a number. Yeah, and communicate it somehow to the rest of the code. What are two basic ways to communicate that something went wrong to the rest of the code? In general programming question. Yeah. Hmm? What? I don't think it's written here. Yeah. Yeah, one method and another old school method that we'll use. Hmm? No, no, no. Debugging is for solving the problems. Yeah. But here it's about communication between the procedures. Yeah. So let's say that one algorithm runs Newton-Raphson's and want to get solution. Yeah. But it diverges. Yeah. So how the Newton-Raphson can tell the rest of the code that it diverges? Yeah. It either can use different method or just shows typically the message to the user, something went wrong, please fix it. Yeah. Which is not very useful, but very common, especially in engineering codes. And one is to raising the error. Yeah, so the code can rise the error, yeah, and then you can catch the error and take the actions. Any ideas? The very old school method, because the first programming languages, as far as I know, not that I remember those times, yeah, uh, didn't have exceptions. Yeah, so you couldn't rise the errors. Yeah, so the typical way to communicate between the units of the program were by setting some flag. Yeah, so you just set some flag, for example, to -1 or whatever the number that you wanted, and this indicates that something went terribly wrong. So the solution that you got is not the correct one. Yeah. Typically, it's better to rise the error, as you described, because it's simply cannot ignore the error. Yeah. while you can ignore flag very easily. You just doesn't check it. Yeah, and you get some solution, and it's a common mistake. Yeah, there are some concerns that rising the errors takes resources, but we won't get into this discussion. Yeah. But in other case, yeah, the method can diverge, yeah. So like here, it can just produce incorrect result, like not a number. It will for sure break your code later on if you use this number. In other cases, it can just run forever, yeah, because it gets, it start oscillating or something like that. Yeah, so it's good to improve it to check for stuff like that. Yeah, and just limit the number of evaluations. Yeah, because as I said earlier, one of the characteristics of Newton-Raphson is that it converges quickly. So if it doesn't converge in like 10, 20, maybe 100, it's huge number. Yeah, but in this reasonably small number of iterations, most likely it will never converge, and we have problem somewhere else. Yeah, so we'll modify slightly the method in a way that it will check if the values are finite and will add limit the number of iterations. Yeah. Uh, so let's take a look on the code once again. What is the name of the file? The file name is simply Newton. And as you can see, whatever you do, okay, it's called APS. I don't like this name, so I will change it. Why? Why I don't like this name? EPS. Okay, yeah, exactly. Yeah, because there's a function, and I don't know if there's a function at all. Yeah, and even you should maybe almost certainly use EPS to set your tolerance. Yeah, but okay. So, but now it's fixed. Okay, and as you can see here, yeah, while our initial Newton method, it's not far from here. It's here. Yeah, was super short, and we can even get rid of this number. And we could even get rid of this, and we could even get rid of this, yeah, by using some programming approaches that MATLAB uses, yeah. So it could be like really 3 lines, yeah. But then when you introduce any kind of checking values and others, it suddenly blow up, yeah. By the way, this is the reason why programming is kind of challenging, and all the programs have tendency to grow super large, yeah. And then you have this very long program, and then in line 6 is your actual algorithm, and the rest is some extra stuff, yeah. But well, this is the way it goes, yeah. So it starts the same. So it's assign x to x0, yeah. Then it calculates value, yeah. So the one change is that it doesn't calculate value multiple times, but because the original function has also this kind of, it can be a drawback if evaluation of the function is long, yeah. But in many engineering, of course, in our practices, memory is not an issue, computations are an issue, yeah. So we typically prefer to use more memory than to do more calculations. Of course, there are domains that is slightly can be otherwise, yeah. Like when you have CFD, I think that they have both issues, yeah, a lot of memory and a lot of computations. But okay. So small optimization that the value of the function is calculated once per iteration. Then we add this iteration counter as described, and because of this iteration counter, our while check both if the value is near 0, yeah, and then if the number of iterations is under our limit, yeah. And here we use this nasty programming technique of magic numbers and set the limit to 100. Other than that, we should just put here a parameter. Yeah, this would be better. Actual procedure is here, line 6, yeah, and then it's checking. We check if it's not a number or if it's infinite, yeah, and if any of those, we show that it's error, and we break the execution, yeah. So comment to user and then setting the flag. If not, then we proceed as usual, yeah. So we calculate value of the function like in the original version, and because we have the counter that we are checking, we have to increase this counter to make this, to make this work. Further away, we are checking simply because here, as it's written, either solution is found, which is great, or we have too many iterations, or the just number is incorrect. Yeah. So now we have to actually check if we have found the solution. Yeah, and the solution is found if the value of the function is, within the tolerance. And if it's not within the tolerance, so this check if the value is larger than tolerance, or it has some strange value, because not a number with comparison always produces false. Yeah. So if you compare two not a numbers, you have false, because not a number, what is it? Yeah. So that's why this is desired behavior. So then you set iteration counter to -1. Because it has no practical meaning, -1. So if the iteration counter is smaller than is negative, then there was clear an error and you cannot trust the solution. And then you assign the solution, and here is just to assign output values. Okay, questions, comments, or this is clear? What? Excuse me?
Variable type is not a number. It's still just normal int or.
So do I understand correctly that you are asking what is the story about infinite, or this not a number?
Variable.
Variable type. No, it doesn't change variable type. The variable type is the same. So, okay, so if I understood you correctly, so we are working with those floating frame representation. Yeah, not floating frame. Floating frame is the method for modeling flexible bodies within multi-body dynamics. This floating precision numbers. Yeah. So those, while, as we described, they have this kind of, they represent it in this limited way, yeah. But there are also special codes, yeah, like the one that shows that if you have just a set of bits arranged in the correct way, it tells you it's infinite, yeah. And then there's another special arrangement that tells you that it's not a number. So the early implementation doesn't have it, yeah. But now, just to avoid some of those numerical issues, those were introduced. Yeah. So if you have variable like here, double precision number, yeah, it can store value like infinite, and it can store value like not a number. Yeah. So still the value type is the same. Okay. Any other doubts, questions, concerns? Okay. So it should work. Yeah, as we described, maybe it should use arrow rather than a flag. Maybe it shouldn't use this kind of magic numbers like here. Yeah, but those are little details. You can almost always, improve your code. Okay, so there should be code demo Newton. Okay. Nothing fancy here. It just uses, by the way, different expression for the derivative of hyperbolic tangents, but they are equivalent. So if we run this with our initial problem, x squared minus 9, and if you run it, yeah, it just shows that it found solution in 13 function calls, yeah, because we are quite far. So, and if we, perfect, comment this and uncomment that, so it is 3 for comment. What is uncomment? Okay, this is uncomment. So if you uncomment this part, so hyperbolic tangent, if we run this, no issues, yeah. And again, if you run it 109, because we check here for a fact if the number of iterations larger than 0, it means solution found. Else, yeah, that we get some error solution. This is how it works. I suppose it doesn't require, yeah.
The solution is immediately on the convergence point. But then ultimately we have 0 iterations.
I don't remember the details, so because yeah, because I choose 9, yeah. Hmm. Yeah, you found a bug in our implementation.
You simply need to make equals like smaller equals 0. Because it's -1, right?
Exactly. Yeah. Yeah. Here's 1 plus number of iteration because it always has to run solution once. Yeah, but you're right. Yeah. Oh, yeah. Again, introducing error if the code is extremely easy. It's hard to find. Yeah, it's extremely easy. But okay. Any more questions, comments? Can we go further? Yeah. One short note, yeah, of course, about symbolic computations for derivative. I suppose that maybe it's even easier now to ask ChatGPT about what is derivative of my function, but I think that I'm not sure if it works, so super well for some complicated functions. But here, if this works, it should be mostly fine, and it's also pretty small. So, of course, uh, finding derivative, it's okay if we have s square minus 9, but again, who remembers what is the derivative of tangent, hyperbolic tangent? Maybe you would remember, yeah? I don't claim you that you don't remember. I simply don't remember. And I would certainly go to search for the web or just use this kind of tools to find it. And if the function gets more complicated, uh, then of course this is the case. And here is this very simple example, yeah, that how to use it in the reasonable way. Yeah. So of course we have to firstly declare the variable as symbolic, then find the expression, simply calculate the derivative, and then you can immediately use it as numeric function. Yeah. So MATLAB function is function that converts symbolic expression into numeric function. Yeah. And then for both of them, and then you can use it already for running Newton-Raphson. As well, here is code that will just save your function into file. Yeah, and of course, if you run it, yeah, simply works. And if you run it with hyperbolic tangent, of course, it works as well. Yeah. Oh, okay, and even there's a question. If you need it. It could be particularly useful when we'll get into computing Jacobians.
I know that CMiM can build certain library, but it doesn't have it natively. Does Java or C or any other one has it? Fine.
Okay, so I wonder how to answer this properly. In short, no, most language doesn't have it. Yeah, I think that most of those symbolic tools are still written in C++. Yeah, and I doubt simply that it's needed. Yeah, because when you have especially the languages like those low level, yeah, C, Java, and others, yeah, typically you have some problems to solve, and this is very unique, and you really rarely need it. Yeah. In your standard work, yeah, and they have to rely on the libraries, yeah. Simply MATLAB is kind of ecosystem with a bunch of libraries, yeah, because in practice, it's not like it's built into the language, yeah. The language is the subset that you have those functions, you have those calls, variable types, yeah, maybe some object, and this is your language, yeah. All the rest, like even this here with symbolics, is the library. And simply MATLAB came as this whole package, yeah. So to find derivative, of course, maybe you are also referring to this automatic differentiation tools. I don't know. Yeah, this is another group of the tools. Yeah, and I believe that some languages might have support for this built-in. Yeah, but the one that is more oriented scientifically. Yeah, I think that Julia might have it, but maybe it's also as a part of the library. So yeah, so I think that there aren't too many languages that have built it in. Yeah, there are mostly for the standard, especially procedural or object-oriented programming languages. There are libraries for it, and of course and the third one is that there are languages that are built on base of this, like in Mathematica. Yeah, so Mathematica language is just built into with the core of symbolic computations.
Things is also a library.
What?
This symbolic.
Yeah,
library.
yeah.
So it's not building.
No, it's not. You mean,
Building library.
Yeah. I also think that it's just like toolbox. Yeah, because if you just get MATLAB without symbolic math toolbox, yeah, then you don't have this functionality. Just simply here at university, we have I think that all those toolboxes, so we don't give it too much thought, but yeah, it's not like granted. But there are, I think, many free also those systems. Yeah, like one is Maxima. Yeah, and if you don't have access to Mathematica, yeah, because if you want to buy Mathematica, it costs quite a bit. And I believe that Python has SymPy. Yeah, that it's one of the most powerful built-in systems for programming languages. Yeah. Okay. More people are sleeping, but the one that not, give it perfectly fine. Okay. Yeah. Now we get into stuff that it's a little more interesting to us. Yeah. So solving multiple nonlinear algebraic equations at once. Yeah. So until now we have one function, one variable. Pretty easy. Yeah. Now we assume that we have n functions and n variables. Can we have different number of functions and variables? Typically we can. Yeah, but it's not very, but then things became complicated because so in practice, we want to solve the problems when those two are equal. Yeah, because if we have fewer functions than variables, yeah, then it means that there is some relation between the variables that it's not defined by functions. Yeah, so something is missing, and if you have more functions than variables, then we can get some contradictory statements, all not very well desired. Yeah. So we'll do the system when those two are equal, yeah, because if, for example, we have fewer functions than variables, we can solve it, but only, for example, in last square mean. Yeah, so on approximate the solution. Here we can, if the problem is well defined, yeah, then we can solve it nicely. Okay, so we'll deal only with the cases when those two are equal. Newton-Raphson method is suitable to be extended to this case, as we will see soon. Yeah, and suppose we have n nonlinear equations of n variables. Yeah, it's just like that. And by introducing vector notation, which makes life much easier and notation shorter, yeah, we introduce one vector bolded f that contains all the functions as column vector. That's why we have transpose here, and vector x of all our variables that is also organized like column vector. Clear? Yeah. I think that you have seen this slide already, Marek, during last week. Yeah, I hope so. Yeah. So we'll use, there are different nomenclatures to be used, yeah, with some underlines, double underlines, and others, yeah. We'll use here boldface nomenclature, yeah. So typically, there are many exceptions, yeah. But typically, matrices are boldface uppercase letters, okay? So they have two dimensions. Column vectors, matrices, and algebraic vectors are boldfaces lowercase letters, xb, yeah. So that's why, like here, we have those lowercase boldface f and x. Scalars as usual lightface letters, yeah. 80 is a row vector because we by default put everything in column vectors. 0 is zero matrix, yeah, of arbitrary size. It can be also zero vector typically. And I is the identity matrix. Yeah, so the matrix that has ones on the diagonal, neutral element of multiplication of matrices. Okay. It seems that there is some questions for this. Okay, let's wait just for like 5 seconds. Okay. Most people get it right, but again, scalars are lightface letters. Yeah. Okay, so thanks to this notation, yeah, we can write the problem in almost the same way. Yeah, so we can write f of x equal to 0. Yeah, the difference is that no longer this or those represent just one entity, but here they represent multiple entities. Yeah. But you can see why using this matrix notation is just much more convenient, yeah, because if you were to able to write all those indices, then, but okay. So let's say that we have a specific example like that one, yeah. So x squared equal to y minus x cosinus pi x, yeah, and yx plus a minus x equal to inverse of x, yeah. Nonlinear equations like nonlinear equation, it has some solution, yeah. And with vector notation, we can write that our variables, yeah, are x and y, okay? And our function of variables x is written that way. Yeah, so we just put, because we want this function to be equal to 0, yeah? So for both equations, of course, we move the expressions into one side and, assume that they will be equal to 0, yeah? So the extended version of this statement is like that. Is it clear? I think that so far so good, yeah? Let's see how it will translate to coding and other stuff. Now, Taylor expansion, yeah? We won't get too much into it, but because Newton's method is based on this, yeah, so that's why here it is mentioned, yeah. So we want to follow the idea from the one variable function, so linearize it and find the root of the linearized function. Clear, yeah. So how to linearize nonlinear function of multiple variables or even single variable? Yeah, Taylor expansion, yeah. We can always, represent the function as Taylor expansion, yeah. And simply, like here it's written, we take this function and we use just first two terms of Taylor series, of Taylor expansion. First term is constant, second term is just first derivative. Yeah. So having f and its derivative at point xi, we can approximate it at some point xi plus 1, which we assume is our solution, or at least it's closer to our solution, by two terms of Taylor series around xi. Yeah. I don't know if it requires any comments. Pretty standard approach of using Taylor expansion. Yeah. So if we limit ourselves to just two terms, we can tell that fx plus I it's approximately equal, yeah, to fxi plus this magical term and just linear combination of those two terms. Yeah, it's totally equivalent to single case. Yeah, when x plus 1 will be value of the function plus derivative times distance. Yeah, any questions? Just standard. Yeah, standard thing about Taylor series. Yeah, so what is this stuff? Yeah, I don't remember exactly this name. If it's the same, because in general it's Jacobian matrix of the function. Yeah, because I would have to check, what is exactly the definition of the gradient. If the gradient can be of the multiple values. Yeah. Uh, so maybe we can check it. Yeah. Uh, so this matrix, functionalized matrix of all partial derivatives of f. Yeah, so it's written like that in short notation. So it's partial derivative of f with x, yeah, while both are vectors. Yeah, so partial derivatives of the vector with respect to vector gives you matrix. Yeah, because then you have to consider all derivative of all the functions with respect to all the variables. Yeah, so this nabla f is often denoted as J because it's Jacobian matrix. Okay, and it's written like that. Yeah, partial in the because f is column vector of the functions. Yeah, so it comes first. Yeah, so all the functions are arranged by rows, and f goes second. So in the columns we have variables. Yeah, so like second row, third column is derivative of the second function with respect to third variable. Okay, so here are the functions, here are the variables. And if you run symbolically Jacobian function, fx, it will produce you exactly this matrix. Okay, So do you have any questions or anyone else?
Probably get it like continue a few minutes.
Okay. In general, this matrix doesn't have to be square, but when it's not square, then we cannot properly solve equations using it. Yeah, so that's why it's another thing why it should be square and has preferably full rank. Yeah, because without those properties, we run into numerical issues. Okay. Another question. So what is the story about this gradient? Okay, I will just check. I don't remember as well. Okay, we have mathematics stack exchange. Let's hope. These are two particular forms of the matrix representation of the derivative.
It's called in line.
Yeah.
It's called gradient. The vector of the gradient of vector.
Yeah, okay. So I think that we have gradient when we have one function with respect to multiple variable, yeah, and then we get the vector. But when we have, like in our case, multiple functions and multiple variables, we have Jacobian. Yeah. So Jacobian, each row of the Jacobian is a gradient. Simple like that. Okay, perfect. In the meantime, the Jacobian matrix represents the gradient of a scalar function and must always be square. Okay, so we discussed it that it must be always be square, but when you have a gradient of scalar function, it cannot because then it's a row. Okay, perfect. Okay, so for our example, yeah, should I maybe solve this by hand? Would it be clearer? Or it's clear enough? It's clear enough? Okay, so good that you are so optimistic. I'm not, but yeah, it's not so important. Okay, so for our examples, then we have again, our variables are x and y, and we have two functions here that depends on those two variables, yeah? So well-defined problem, at least at glance. So our Jacobian, number f, first row, first function, second row, second function, first column, first variable, second column, second variable. Yeah. And just by writing partial f1, partial x, partial f1, partial y, and so and so. And now we just have to solve it. Yeah. So partial f1, f1, partial x, because x is our first variable. So of course, this term in our matrix is 2x minus, okay, this disappears. And firstly, we have cosine by x, yeah, minus, because cosine gives us minus sine x, and pi gets here, yeah. Pretty simple because we have simple functions here. And of course, second number is -1 because we have partial f1 with partial y, yeah. And y appears only here, and the relative of this gives us -1. Set. Second row, second function with respect to x, yeah. So here we have second function, yeah. And with respect to x, here x appears, so we get only y, no x, no results. And here we have -1 in front, x, this gets -1, so plus x minus 2, as is written here. And partial f2, partial y, partial f2, partial y. So again, from here we get x, yeah, and from this a minus y, we get minus a minus y, as expected. Okay, yeah. So we just get Jacobian, yeah. Now, if we have function if we know what are our variables, if we have Jacobian, and then if we add those starting values like initial values of functions and tolerance, we can solve this nonlinear equation using Newton-Raphson's method. Yeah, so by using Taylor expression, we can have this. Yeah, so with approximation of xi, yeah, so of course we need some starting value to the root. We seek a new, hopefully better approximation of this problem, fx plus 1 equal to 0 by a linear function. Yeah. So again, expression of Taylor representation of Taylor Taylor series expansion of our function around new point. Then we can rewrite it as linear set of equations, solve it for delta, and with delta we can get the new approximation. Yeah. So it's almost the same like in the scalar case, but we have to, just take care of this. So the algorithm would be like that each step of this Newton-Raphson iteration consists of two steps. Yeah. So solve the linear system with respect to delta, and then set the new value. Linear system as usual is solved using variant of Gaussian elimination. Is it clear? So do you know what is the most typical method used for solving this kind of problems? How it's called, the numerical representation of Gaussian elimination that is typically used? Have you had some numerical methods in the past? Yeah, but it was a long time ago. Or maybe they haven't asked about it. So have you ever heard about LU decomposition? Yeah. So typically for general matrix, yeah, when you decompose it, the variant of Gaussian elimination takes form of LU decomposition.
Upper.
Well, lower and upper. That's why it's LU. Yeah. Lower triangular and upper triangular, yeah, decomposition. Why they use this? Okay, yeah. I think that we don't really have to get into too much details. Yeah, there are also another decompositions depending on the characteristic of the matrix. Yeah, like have you also heard about Cholesky decomposition? Yeah, that is valid when the matrix is symmetric, positive definite. Yeah. And the reason to have multiple decomposition is that simply, Cholesky decomposition, is more efficient to solve than LU decomposition, yeah, because it uses lower triangular matrix twice, yeah, because of properties and so, yeah. Of course, you can write it, but it was written like decades ago, yeah, and MATLAB typically uses well-known LAPACK package for this purpose. That it's written in Fortran by scientists many years ago. Yeah, and in MATLAB typically it's used by this this backslash operator. Yeah, and I put here that you don't use inverse to solve this kind of problems because you don't need inverse. You calculate inverse when you need it. Yeah, and simply using Gaussian elimination is just faster and more accurate. So that's why if you So one thing is mathematical notation, and another thing is implementation, and quite typically those two are far away from each other. Also know that Jacobian is often sparse matrix. So sparse matrix, it means that it contains mostly zero elements. Yeah, if we have huge systems, yeah, typically huge systems are arranged in the way that each function depends only on a few variables. Yeah. So then we have a lot of zeros because of partial differentiation. And in this case, there are special methods that can be used. Have you ever heard about sparse matrices? Okay, perfect. So how what is the difference between representation of the dense and sparse matrices? Yeah, so yeah, okay, so compresses. No, so now we get too much into details, yeah. But for the dense matrices, simply you are storing all the values, in the memory, one after another, yeah. And for the sparse, you just totally change the representation, yeah. And one of the easiest representation is that you store the information about the index, yeah. So you use for each entrance three numbers, yeah. You use index, yeah. What is the row? What is the column? And then what is value? Yeah, and then you eliminate the need for storing all those zeros. Yeah, and in large, big enough problems, this saves space and saves computation, because of course it would be wasteful to use it for dense representation. Yeah, because just storing one number after another is more efficient than if you have to add index to it. But okay. And I think that we have the last, yeah. We have here the very last question for this series. Okay. Still, the correct answer wins. We have quite a few others. Yeah. Then calculating inverse, yeah. Calculating inverse takes quite a lot of effort and steps. And Gaussian elimination is just one step to calculate inverse, yeah. So then you have to also solve for it. So, hmm? What? Could you?
As it's really easy matrix to inverse.
But it doesn't matter for numerics, typically. Or do you mean that you can inverse it by hand? Yeah. Or use symbolic computations, then it takes ages to inverse it. Of course, in the very simple cases, yeah, maybe it is doable, to use it symbolically, like here and then. For multiple uses, it will be faster, yeah. But if you rely on symbolics, yeah, solving the system, I think it's always faster, because simply less operations are needed, and you tackle the problem just directly. But again, to verify those claims, yeah, if it's faster, not faster, then at least we should benchmark it here. But yeah, I think that we can skip it. We have benchmarking other parts. But yeah, checking those claims, typically it's good to benchmark things, because many such claims are context dependent. Okay. And here we have simple hands-on. Okay, maybe it's not so simple. Yeah, but we have hands-on that will combine, or I don't know. But however, yeah, let's see. I suppose that, we should also take a look on some implementation before we will get here. Yeah. So firstly, here is the implementation of the Newton-Raphson method, that it's based on our a little more or on our robust Newton's method implementation. Yeah. So for this method, yeah, we're assuming that f and j are respectively a vector of functions, and the j is Jacobian, and x is also a vector of initial values, and APS that we don't like. Again, let's install. And let's go quickly through the code. So as for the Newton method, the code is mostly similar, yeah. So we just keep the checking for not the numbers and infinite values. It will most likely just stop or use iteration counter. But okay, so a function value, we calculate the function value. Then in the linear case, we have absolute value, but here, because we are dealing with vectors, absolute doesn't give us required quantity, so we need to use some kind of the norm, yeah. And by default, this is L2 norm of the vector, okay. Iteration counter and procedure is similar, yeah. We check if the norm is within the tolerance. And if we haven't, and if we are within the limit of our iterations, then we have those two lines that are described on the slide. Yeah. So the first one is to solve for delta. Yeah. Exactly like here. Yeah. Using this ML divide operator. Then we update our solution, just like in the step 2, x equal to x plus delta. Yeah. So we are updating our solution, hopefully getting closer. And repeat. Calculate value again. We have to calculate the norm of it, increase the iteration counter, and repeat until we get the solution. And here is the checking that if solution is found, the norm of it is within the tolerance, and if it's not, then iteration counter is set to -1. Questions? Makes sense that it works? Yes, we can. We could. Yeah. Then instead of checking the norm, yeah, you would actually calculate the absolute value of all the functions, yeah, then compare it with tolerances, and then tolerance has to be also, for example, a vector, yeah, and then you will get the Boolean vector, and then you can check, for example, that all values in this Boolean vector are true. And then if all are true, you know that all respective values have given tolerances, yeah. I think it will be more common to go other way around, that instead of assigning different tolerances, you will scale your equations to be in the same range, yeah. So I think this would be more common, because then you are also avoiding the round of errors when you process your numbers. But yeah, it's quite common, yeah. Like here, for example, in this mechanism that came next, yeah, we have, even here we could have different problems, yeah. For example, if you have, because here we have mixed set of coordinates. One is about, one is in angles, and we will most likely represent this in radians, and another is distance, yeah. So if we have the same problem, but this is in micrometers, yeah, then we can run into issues, yeah, because then radians are like always radians in the range of 1, yeah. But if this gets to something like distance in micrometers, that it could be an issue, and then you have to scale something to make it well conditioned, yeah, or even picometers. Then it could be a disaster. So yeah, so scaling and, for example, using same means of dimensions or even dimensional values, it's often a good idea. It brings a little complexity, but then it makes the code safer. Okay. So this is about Newton-Raphson iteration, Newton-Raphson method. Yeah, so nothing particularly strange. So what there should be some yeah. And here is how it looks like when we put this example from here, because this is our example, into the code. Yeah. So here is our function. Yeah. That is function of x. X contains two variables. Yeah. So of course here we use it nicely x and y, but here it's written as x1, x2. Yeah. Because I use the short, it can be used xy, but then we have to expand it a little. It's possible. And here is the first function, and here is the second function. Maybe it should really be written in the nicer way. Is it readable? Kind of. Yeah. Maybe it's more readable if we do with this. I think that I prepared all this even for the times when the MATLAB doesn't support this kind of function with the scripts. And then we can write that x is equal of xv of 1 and y is equal of xv of 2. Because using those anonymous functions is quite handy. Then, code is short, but it's not so readable. Yeah. And then we have simply that result is equal to, okay, so it's x, y, x, and x. And the second is x times y, y, yeah, I suppose that this part is more readable. Because then we can clearly see relation between this function and this code. Yeah, and it's even easier to spot the errors. Yeah. Of course, I have to then, yeah. So then we have to remove this part to work. Yeah, now it doesn't show this error. And of course, I have to put here different naming like xv to be able to use x inside the function. So let's do the same for the Jacobian to be consistent. xv, then we need those two same lines, xv of 1, y is equal to xv of 2. Programming is difficult enough not to make it even more difficult by using some kind of convoluted and obscure codes. The second term is -1, and here we have y, x to -2. Here we have x. And here is y. And now let's check it. Here is our Jacobian. So it's not so easy to check it, but 2x plus cosine pi x minus pi x sine pi x, okay? And the second one is y minus x to -2. Seems to be valid, -1, okay, x minus x minus 1, okay, seems to work. And now it's written in the form of test, so it's expected to be 1, 0, yeah, with tolerance of 10 to -4, okay? And then we run Newton-Raphson method with initial values 2, -1. Then we check if the value is expected, and if it's not, then we throw an error. Okay, so let's run it. Not enough input arguments. What I have done incorrectly. Okay, I know what I have done incorrectly. Okay, and now it works. Yeah, because earlier there were variables. Yeah, so this just works because of passing variables. Yeah, but because of how MATLAB works, you know, if you just declare a function to make it into variable, you need that add. Yeah, so not very intuitive. Error comment, but okay. So it works, and you can see that the error is below the tolerance for both variables. Yeah. So the value that was returned x from our solution is exactly the one that is expected. Near to 1 and near to 0. Okay. Any comments to it? Can you go further? Perfect. Okay, so this is the last point of our meeting today. So this hands-on on simple mechanism. Yeah. So the task is to use Newton-Raphson method to find angle phi 2 and distance d. Yeah. When this angle is provided. Okay, is it clear? Yeah. So we know what is the angle here, and we wonder what is the angle here and what is d. Yeah. Here we have some extra information. Yeah. About our system. So we know what is distance A, we know what is distance R, and we know what is distance B. How to solve this? It's written here that we should use Newton-Raphson method. Yeah. So we know what are our variables that we will look for. Yeah. So we look for phi 2 and d. We know what is provided for us. Yeah. So to solve this, we need some equations. Yeah. How many equations do we need? Yeah, of course. Yeah, we need two equations because we have two unknowns. Quite intuitive. So how to write those equations? Any guesses? Exactly. So how to write it based on this figure? Oh, no, we don't want to deal too much with trigonometry. Of course, we still have to do something, yeah. But yeah. Something like that, maybe. Yeah. Oh, yeah. Yeah. Okay. Yeah, so it can have different names, yeah, but we want to, and we can here pretty easily write this closure equation. I think that you already, Marek should mention this, yeah, and that it brings one of the solutions, yeah. Simply, it means, can I draw here something? Maybe it won't be nice, but still it could be useful. Draw. Yeah. So I don't know even what will be the best way to draw it. Yeah. But if we have here one vector, we call it vector B. Yeah. Then we can have here vector A. And of course, now everything is shown, but yeah, how to get it. Yeah. So this is vector A. Yeah. Then here we can have vector. Let's call it vector R. Yeah. And here is the last vector. Let's call it vector D. Yeah. Okay. And then, of course, if we write that B plus A plus R, yeah, plus, maybe even if it's not readable, I hope that with my comment, then it became quite clear what we are dealing here with, plus D, yeah, is equal to simply 0 vector. This is clear, yeah, nothing fancy here, yeah. And here we can get quite general rule, yeah, that for this mechanism, yeah, it has here this kind of the loop, yeah, because if we idealize how are the joints and this point, yeah, it will be always met. So for this kind of planar mechanism, we always can write this kind of the loop. We have more bodies, then we can write often more loops, yeah. But if you have this kind of simple mechanism, we can write one loop, and one loop gives us two equations. Yeah. And because it's vector equation. And those two equations gives us this set of equations. Yeah. And then it works as it should. Yeah. So here is the problem. And here is the statement. Yeah. So this is B vector. So of course there is some bit of geometry because this is in the first, then we cast it on our XY axis. Yeah. So then we cast it on X, Y. I hope that I haven't missed them. The axis, yeah. Is it X? Here is cosine. Yeah, I think it's okay. Yeah. So then we put it in this form on our two axes, yeah, and we get this kind of equation, yeah. So this is B vector. This is A vector. Yeah. Make sense? Yeah. Uh, mm, uh, this in practice is the form of R vector, yeah, because X for R vector is 0. And this part is our D vector. Yeah, because for D vector, Y is equal to 0. Yeah. And without getting into all those details, we have those vectors. Because of how it looks like, we know that this equation is met, so we can put it equal to 0. Okay. It's not very complicated. So it's super easy to write Jacobian matrix for it. Yeah, we just differentiate it. It's not written here. Then we'll get to some assignment. So maybe I should also write it. Yeah, that what is our vector u? What is u? How it is? What is u? Yeah, but what is it? Okay, you're right. Yeah, so u is our vector of unknowns. Yeah. And exactly as the name states, is a vector, yeah, and it has two coordinates, yeah. It has phi 2 and d. Yeah, and we need the information about u. Of course, it's relevant here, but we need also here to know how to make the Jacobian matrix. Yeah, so this is first function. Yeah, so first row, and with respect to phi 2, yeah, and phi 2 is only here, so that's why cosine minus sine, so minus a sine phi 2, yeah, and here also phi 2 is only here, so we have a cosine phi 2, yeah, because here is sine gets into cosine, and here this is with respect to d, so minus 1, 0, okay, and it's written that it's 0, and it's of course this part is incorrect, so I have to fix my slides, yeah, because it doesn't make sense, because Jacobian is not equal to 0. Then it can be just misleading. So, okay, is all this clear? Any doubts? Any questions? So, can you now write a simple code that solve this system? Take a few minutes and try to solve it. Can I share with you how to share with you files? Because I don't want you. Of course, I want you to use Newton-Raphson method. Yeah. So I'd like you to use those. Yeah. Is it okay if I will share it on Teams? Do all of you have access to it at the moment? Hmm? Yeah, but I will share everything on Moodle. So if Teams works now, because not to make the mess with the Moodle, yeah, I will put it on the Teams chat. So I will stop sharing it for a second to edit to add those files to chat. Open it in Finder. We need maybe those two. Where is? Yeah. Okay. So I hope that you can download the files. Yeah. Let's get back into sharing mode. Yeah. So now I shared with you two files. So Newton-Raphson implementation and an example, test example of how this Newton-Raphson was used. Yeah. And now your task is to use those two files, modify the test to write it totally different, and implement what is shown here. Okay? And let's have a few minutes to do this. Yeah. Can you access the files? Everyone that is interested? Okay, there's some issue with those files. I will put it on the model as well. So here's our course. Then I will remove them simply to make it. Then I will remove them from this topic most likely when I will upload all the other files. Yeah. So. mm. Okay, so now the files are also on the model. Okay, if it's easier for you. And so now I will leave you for a few minutes with Okay. Are there any questions to the problem? Yeah, it's a valid question. Yeah. Okay. I think that it was not an issue for our online participants, but the values that are here were hidden because of Teams window. Maybe other question. Is it clear what need to be done and how to do it? So of course you have to code this as a function, yeah. Then this is Jacobian of this. Then you have this value, which and with other values, it allows you to write this function as with only two unknowns. All the rest can be put it there. Same applies to Jacobian. And then you can just call Newton-Raphson method to get value for angle and displacement. We can still have a few minutes to solve it.
The values are square, so strange values. Oh, so it is angles. Angles. Oh, that's okay now. Yeah, it makes sense. The distance, yeah, but if you solve it in angles, we're going to take care. Yeah. Because it can be in angles, but then you have to use this cos D and sin D. Yeah. Because by default they work with radians, and so you have to convert it to radians. Yeah, so you make some new arrow. And yeah, for sure, you make some error. Where is the check out? This is. Oh, it's the yeah, some yeah inverse. Yeah, inverse of finding of some strange values. Yeah. Why? Yeah, now it's better. Does it make sense? Why? What's n? What's n? And why is so high? Why do you expect why 1 and 0? Because you also what? Your code will also this. Yeah. So and there's okay, but but code for was for different stuff. Yeah. So why do you expect y and 0? Where is 1? This one? Yeah. It should be 30. But how do you know what to expect? Have you solved it by hand? No. Should I don't know, but if you write expected value, then yeah. And does it make sense to start with this point? Zero. So you think that yeah. 0 and 1. So do you think that the D can be 1 by looking on the image here? No, it cannot, but it will improve itself. Yeah, but it can not be less than. So you cannot do better? Can you do better? Can be cos phi. Cos phi is cos phi 1. Yeah, but I think that don't have to be so accurate, but still having it 1 is really far from actual solution.
Cos 30 is, I think, 0.7. And what do that will be? No. B line.
You know, even 10 is much closer than 1, because as you said, it cannot be 6. It's 6. Yeah, I would put 10 or 12, yeah. It's still much closer.
But I will move this thing to edit.
And then you have error here.
No, this is like error is. It's not an error.
Yeah, but you have error, it's called.
Okay.
Yeah.
I don't understand. Isn't it the same as when you recently says this 400 must be scalar? Or error is just a normal vector?
But why do you have this code here? Like that. What do you need authors for your solution?
No, it doesn't have a bit much. Of course, call it out. But switching between columns.
I don't have a unit test.
So, yeah, you should just remove it. Remove all this, yeah. Because, even when you copy paste the code, yeah, I don't. You should, I think that copy the parts that makes sense. And all this error measure, it doesn't make sense. Why do you leave it here? But it doesn't make sense.
This one?
Yeah, it doesn't make sense. What is the meaning of this error? Theoretically, commented that way, but what is the meaning of it? Physical meaning. What is physics behind it?
It is like
Error of what with respect to what?
the one expected and but the one that returned.
So how do you calculate expected value? So we get back to this point. Because if you are expecting something, yeah, so you are expecting something, so you are expecting that it will be 1 and this not to be 0 for this problem.
Yeah, we know the exact value
How do you know it?
by the equation.
So you put it 1 and 0, so how do you calculate the distance to be 1? Or angle to be 1, yeah, because it's a lot of mysteries here. No, you should just use the code that makes sense in your problem, yeah. So, and this line doesn't make sense to me.
Let's degree.
Yeah. Whatever, why do you comment that? Will it make sense for later?
Choose.
Yeah, now it makes far more sense. And is solution reasonable?
Yeah.
Yeah, solution is now reasonable. Because what is important to know? Programming is a tool, so you see what the basis behind it.
Yeah, so but they were degree direct.
Any questions? Of course.
Of course.
Of course.
I don't remember how to state that the is a
You remember it, at least no. But what is U0?
and then you submit.
Yeah, but you put it incorrectly. But you think that the distance is fine? I think that the inch of distance is fine. Anyway,
Yeah. I'm using the.
Okay.
do you think that the
No,
5 meters?
No, yeah,
What your error is that you have to use here a semicolon.
he's giving me a.
F. So function F is unknown. F is your variable. So we're running those stats and check it here. How it works. Does it run maybe? Still not.
The newest function.
See.
Yeah, because I believe wrong. Yeah, because I copied the problem as the I.
Oh, yeah,
Conversion.
you assign the variables
Yeah.
correct. So this is the issue. Because phi one is given.
And
Does it work for you? Fine.
these functions. Right function.
So first you have put the function equation correctly, because I think that now we have a vector of function, and I doubt that you wanted to have it. And because you go to the functions into your vector.
We define a function and we define the functions in the vector.
So then you have to resolve it. So when you address your vector, you get a function. So this was the issue. And so this is one problem. And the second, then if you list the number, list the variables after you comma, and you cannot address it with a single variable. And the function expects a single variable. Okay, so there are many causes for the issues. Can but that is you have solved it finally for it. It's good. Solve it. And do you have any question? Okay. Okay.
So because we have to end our lecture, yeah. I believe that, I'm pretty sure that I forget to update that one. No, I updated them. Okay, that's nice. Yeah. So, by the way, I think that here I have example solution for it. So you can check it if you weren't able to solve this. Yeah. So I will attach it, but here we have, assignment. Yeah. Based on the last 2 weeks or a little more. Yeah. But the one is from Newton-Raphson book. So I will share with you on Moodle, of course, assignment and the part of the Newton-Raphson book. Yeah. And this part is connected with the lecture that was 1 week ago. Yeah. About the mechanisms, about degrees of freedom, about the coordinates and stuff like that. Yeah. So you can take a look about the very basics of multi-body dynamics in planar case, yeah, and solve some problems that are related to them, yeah, particularly to those choice of coordinates and similar stuff, yeah, a little about maybe constraints. And then PDF of the solutions, yeah, so you can solve it however you like, of course, in reasonable way, yeah. But I suppose that the easiest way is to just put it on the paper and then scan it and send to me. Okay. Any questions? And the second one is very similar to the task that you have just solved. Yeah. So here is slightly different mechanism. Yeah, but still very similar. Here is a loop equation for this mechanism. Yeah. And as you can see, like phi is given, omega is given, those distances are given. And the question is, what is this angle? And what is this distance? Yeah, OB distance. Yeah, so OB is equal to D. Yeah, so very similar. Yeah, the difference is that in this last case you have this this disk there, and here is just a slider.
This does not need to go.
What?
This does not need to go to the report.
No, it's second report. Yeah. And the difference is that of course you solve it for x, yeah, and then solve it in time. Yeah, so you solve it because you have phi and omega. So of course phi is a function of time, as physics shows. Yeah, so omega is constant, but so it means that you know how phi evolves in time. Yeah. Yeah. So you can solve it for 1 second. Yeah. So you solve it for 0, store value, solve it for t equal to 001, and progress with your solution. Yeah. So you have to write loop in time. Like here, you have loop in time, store all values of x, and then make some nice plots of how d and theta changes. Yeah. And here you can also differentiate it with respect to time easily. Yeah, because I suppose that writing, knowing how this f dot of this, it's not a big deal. Yeah. There are just some simple trigonometric functions, and you know what are variables that change in time. And then you can also solve this for x dot. Yeah, so you can provide what are positions and what are velocities of this kind of mechanism. Yeah, we won't bother with accelerations this time but this is also very relatively straightforward. You just calculate f double dot, yeah, and then you can solve for x double dot. But okay, but this will be for the future. Is it clear? What is asked from you? Okay, perfect. And yeah, exactly. So solve the problem from the previous slide. Oh, even phi is given here, yeah. So pi 6 plus omega t, yeah. Create plots for t versus angle theta, displacement d, and their time derivatives. Write report, and the same, yeah. Then you have, a big chunk of it. It's already solved for you. You just have to put it into the loop, calculate one time derivative, and include this in this loop, and store values and make a plot. Any questions? If not, then we'll see in 1 week. You looks like you have some concerns. Does it look too easy to be true? Of reports?
Yeah.
Yeah, it's maximum. You can write it much shorter, yeah. Yeah. So as I tell you at the start, yeah, most of you write the reports that are too long. It's okay, yeah. Yeah, it's not a problem. Yeah, I mean, not too long, of course, because here are the requirements like 2 pages, so they're not too long. But it will be okay if it's, like this kind of report should easily fit on half page of text plus some plots. But okay. But yeah, thanks a lot. Yeah, and we'll see in 1 week. So let's stop the sharing. Let's stop the recording. And yeah, so bye.